So, when we're talking about dating fossils, again, this page seems fairly straightforward, but I want to make sure that you understand some of these terms. Let's start with fission track. So, fission is this process by which an atom breaks up into two separate atoms, and the protons and the neutrons. The nucleus is unstable, and when it breaks up into two smaller atoms. In the case of uranium, that in the case of all radioactive material, these particles are moving at high velocity when fission happens. And if it happens inside a mineral, sometimes it leaves these little streaks, these tracks through the mineral. And with a microscope and knowledge that I don't have, you can analyze those tracks and help date a rock. So when you look at fission tracking, that can go. You can track. You can look at the age of rocks all the way back to 100 million years ago, anywhere from a few thousand, 5,000 to 6,000 to 100 million years ago, depending on how many tracks there are in that particular rock. Because obviously, the more tracks there are, the more fission events occurred, and since the fission occurs at a relatively predictable pace, you can use that as a clock, as we discussed in a previous video. So radiocarbon dating is when you have carbon-14, how much of carbon-14 is left. Now here again, when you're looking at carbon-14, carbon-12 is the non-radioactive form. The stable form, carbon-14, breaks down, and becomes other elements, becomes radioactive, breaks down. And as it does, it's going to be less and less. There's a proportion of carbon-12 to carbon-14 in any organic material, and that proportion of carbon-12 to carbon-14 can tell you how old that material is. The older the material is, the bigger this number, because the more carbon-12 there is and the less carbon-14 there is. So as you're looking at radiocarbon dating, that works anywhere from a few hundred or 1,000 years ago to close to 50, 60,000 years, 100,000 years. Potassium argon here again is radioactive potassium, or potassium-40, breaking down into, it turns into argon and releases other subatomic particles. Argon, and in volcanic rocks, and that's really good. That's really good for dating rocks going from anywhere from 8,000 all the way back to 100 million years ago. So fission tracking, potassium tracking does a good job in those date range. It's usable in those date ranges. Uranium series is where uranium turns into thromium. Again, what happens is these things break down. Uranium-235 breaks, and 238. Those are two different radioactive elements. They can break down into thromium, and another isotope, uranium-234. So they can break down into two elements, thromium-230, and they can break down another isotope called uranium-234. So again, through various methodologies that they've developed, the physicists have developed, geophysicists have developed, you can track the age of organisms that have this uranium back from, not organisms, but rocks that have this uranium, fossils that have this uranium, all the way back from, a few hundred years ago to 1,000+ years ago back to a million and some change. Paleomagnetism is good for older rocks, anywhere from 100,000 plus to 100 million years ago. They have to contain iron, though, and this uranium series is good for mollusks, any carbonates. Obviously, this one's for volcanic rocks. Volcanic rocks and minerals obviously won't have any fossils in it, as we discussed before. Things that have been become molten as part of the magma of the asthenosphere, or as part of have entered a volcano, they're going to lose all their structure as they melt. Wood, radiocarbon is good for anything with carbon in it, any organic material, any wood, bones, any animal tissue, anything that has living tissue or living. It comes from living material. Fission tracking is good for pottery and glass and volcanic minerals. And so you see that each of the materials has their own method of dating these ancient artifacts. So paleomagnetism, again, is older. We discussed that method and where that comes from. A second here. Thermoluminescence, it measures the amount of light emitted from quartz or zircon that's been exposed to sunlight or in the distant past, or fire. That's really interesting. I'd never heard of it, so I'm not sure why it would, but I do know that materials do absorb energy and they release energy. That there are luminescent rocks that glow in the dark. There are, you know that there are toys and even paints that you can get that can absorb light during the day and emit light at night. We know that there are bioluminescent creatures that do it in just a slightly different way. So thermoluminescence, the idea that these quartz containing rocks like flint, that they can emit a certain amount of light depending on the last time they were exposed to the sun or to a fire. That's interesting. So if you find rocks that are very deep in the earth and you dig them up and you go through this thermoluminescence process, which I'm not familiar with, I'm assuming you can measure then how long ago it was formed, or how long ago it was exposed to sunlight or heat, or fire rather. So that's interesting, because that would suggest that it was on the surface of the earth. Somehow they're able to come up with a date from a few thousand to 100,000 years ago. Electron spin resonance. So as you may have learned in Mr. Custer's class, as electrons are in orbitals around an atom, and they have what chemists and physicists call a spin, and two electrons in the same orbital have opposite spins. And they have opposite spins because obviously two electrons are going to repel each other. They're both negatively charged, but they're taking up the similar space. They're very close to one another, relatively speaking. So what they do is, in order to reduce that repulsion, they spin in opposite directions. So the spin on these things, I'm not going to pretend that I understand all the details here, but the electron spin resonance measures how much microwave energy was absorbed by the samples previously heated or exposed to sunlight in a distant past. So for some reason or somehow, these electron spin, they're able to use this electron spin to measure how much microwave energy can be absorbed by material, right, that's been heated or exposed to light, very similar to thermoluminescence, except they're going to look at the electron spin, the direction of the electrons in a machine, and be able to date the rock. Again, I'm not familiar with the process. I think that's obvious. Amino acid racemation. So there you're dealing with the conversion of amino acids from left to right-handed amino acids, and that has to do with the orientation of the amino acid. So remember, we talked about amino acids that have the R group sitting out. You have a central carbon. You have an H group. You have the carboxylic acid group, C double bond O, single bond OH, and then you have the amine group, which is the NH2. So whether this is right-handed, in other words, it's the R group is pointing in one direction, or it's pointing in another direction, left-handed, is a matter of time. They'll flip. The R group will flip to the other side in a fairly predictable amount, in a fairly predictable time period, again allowing you to use it as a clock. We call these isomers, whether they're on one side or the other side, whether they're here or here, we call them isomers. So if you have the R group on this side, you call it one isomer. R groups on this side, you call it another isomer. This amino acid racemation, and what they mean by that is that you're going to have 50-50, or you have 40-20, or you have 20% right-handed, 10% left-handed. Do you have 50-50, or do you have 60-40? Whatever the percentages are, tell you how long the amino acid's been around. Now, amino acids are not like DNA. They actually last a lot longer. They're much more stable. Amino acids are much more stable, so they can last a pretty long time. You can use amino acid racemation going back 100,000 plus years. Verve looks at the deposit layers of sediment found in a lot of lakes. They're called varves, right? And varve, you're going to look at, and obviously you're only looking at glacial lakes, the lakes that were produced by glaciers. How much material was layered on top of the bottom of the lake as it was formed, and that tells you something about how old that rock was. And so you have going back about 10,000 years that works with. I'm not sure if the Great Lakes you'd still be able to measure this varve, but they were carved out by the glaciers. Tree rings, counting the tree rings. I think everyone's heard of that. There's a ring for every ring is a year. But when you combine that with carbon dating, that lets you go back even further, so you see how old that tree was. If it's 100 years old, and then it goes back, and then you do the carbon dating, you find that particular tree has X percentage of carbon-14, then you can tell, relatively speaking, how old that tree fossil is. All right, so you should be able to tell here how to fill this up. This is pretty much just reading the table. All right, but when we're talking about any of this dating, I think it should be obvious that we're talking, and if you take a look at the ranges they're saying 1,000 plus years to 10,000. They're not giving you exact dates. They call them absolute dates, but they're not giving you exact dates. They give you a range. They can tell you, well, this method works for up to a million plus years ago. When you're given a date, they're generally telling you, look, I can tell you within 100 years, or within 1,000 years, or within a million years how old this rock is. I can't tell you exactly how old the rock is because there's no way I can do that. I can tell you that it's about 1 million plus years old, given that it takes this long for this radioactive material to break down over this amount of time, and this is how much is left. So I'm going to tell you the rock is at least this, but no more than that. So often what what they will do is they will give you numbers with a plus or minus, let's say 50. So that's telling you that within a range of 50, this is the number. So on a graph, for instance, you might get something like, you might see some points plotted on a graph, and maybe this is 10 and this is 20, and on that point you might see a little, what they call a whisker, right? It might come out to here. That's letting you know that this is the data point. We're pretty sure it's 10, but there's a plus or minus here. It could be as little as, this is 20, but it could be as little as 15 or as much as 25 on the accuracy of that measurement, or the error we've calculated is within this particular amount of there's this amount of error to this measurement, this particular measurement. And each of the measurements, through various statistical analyses, can be, you can add those what we call whiskers, letting you know that there's an error, there's an amount of error with every measurement that we have to consider. Obviously, when you're talking about measuring the age of rocks and fossils that are millions of years old, that error is going to be pretty big. So when we're talking about, again, they're going to use this plus or minus, right? So if they tell you, well, this particular dinosaur bone has been no, dinosaur bone wouldn't be radiocarbon dated. Let's see, what would they use? All right. This, I'm looking to see what they would use here. All right, so let's just say this pollen was found in a rock sample, and we're thinking it's 15,000 years old. So let's just use 15,000 years old, and we think that's give or take 5,000. So we'll say plus or minus 5,000 years. So when we're talking about this particular dating event of 15,000 years old, it could be as old as 20,000 years. So it could be 20,000 years old, or it could be 10,000 years old, or it could be 15. It could be anywhere in between. They're not sure. They measured it at 15, but there's a plus or minus of 5 on either side. So again, in science, we do our best to get it as accurate as we can. However, even though we're pretty sure that we got the range correct, we can't be sure on the exact number. So there are a lot of events that could impact how old the rock is, right? There could have been events that occurred throughout the geologic history that somehow changed the amount of radioactive material available in the rock. There could have been all kinds of things that it could have changed. There could have been a plume of radioactive 14 in a particular area that allowed the living material to. I mean, I'm just spitballing here, but there's 1,000 things that I can imagine that could go wrong when you're talking about radioactive dating. It could be experimental error, but that's doubtful since they'll repeat their measurements over and over again. the decay rate is pretty consistent. We've discussed that decay rate of radioactive material is consistent. However, how much radioactive material there was in the particular to begin with is a question. I'm sure someone's addressed. And in any case, you're talking about averages. You're talking about millions of years. So there's going to be some error in that measurement. There's going to be some events that you can't even predict. You can't some confounding event that you can't even predict that's going to impact that particular measurement. So if you're asked, what could be some of the errors in radiometric dating, well, then you could talk about things like the material, right? The radioactive material could be added after the rock was made. By geologic processes, right? By magma entering the rock and the uranium seeping into the rock. I'm not sure how it would happen. I'm not a biochemist or a geochemist. You might have if different geochemical events occur, right? I'm going to call them geochemical events. Chemistry that I'm not aware of that happens in a volcano or in a magma chamber or in rock that's next to a lava chamber or magma chamber. All these things could change, you could adjust, could affect the accuracy of your measurement. But even though that's true, note that the error is generally plus or minus a million years, and that sounds like a lot. In fact, it sounds like it's so much that why do we even bother? If you're going to tell me it's between 6 and 7 million years ago, well, man, that's a million years. There's a lot of things that could happen in between there. However, if you think about it, if we're talking about 3.5 billion years, and you're talking about a scale that what we're really looking at, what we're really thinking about is if we find shells here and we find, pollen would be up here, pollen here, and we find jellyfish here, then what we'd like to see is that the jellyfish is older than the shells, is older than the pollen. If it's going to match, if the theory is correct, the theory would predict that the jellyfish rock is going to be older than the shells. If the jellyfish is an older species, right, an older species of jellyfish, and the shells would be older than the pollen. Otherwise, then the theory of evolution would be in question, right? Assuming that these are the older species and these are the younger species because of structure, right? When we look at the fossils. Because obviously there are shelled organisms alive today, and there's pollen today, and there's jellyfish today, so we could find these things living in our world today rather than just fossils. But what we would see is that even though this one is, let's say, the process says it's 12, and this process says this is, let's say 112. I don't know. I'm just going to have to come up with some numbers here. But let's say the jellyfish is 500 million years old, and they're in rock that's 500 million years old. We find jellyfish imprints. It's probably too old. I'll just go ahead and say it, and forgive me if I get the numbers wrong. I don't have the various numbers memorized, but and then the shells, and you would say that the shells are 430 million years old, and the pollen is in rock that's, I don't know, 200,000 years old. But you're measuring the age of the rock with a plus or minus of 1 million years in this process, so that's plus or minus 1.2 million, right? And this is plus or minus 1.2 million. And this is, you're using a different method, so maybe this is plus or minus 10,000 years. Million years. So when you're looking at the age of the rock, yes, there's error. Yes, there's things that could go wrong with the measurement, and there are predictable things and there are things you can't predict. But when you start looking at where you find it in the strata, the relative dating, and then you compare it to the absolute dating, and then you compare it to what you had predicted with DNA evidence as far as how much DNA is shared between these organisms, and how old do you think, which one do you think is older? Once you put all that evidence together, if your explanations are reasonable, then they should all match up. They should all support each other. If one contradicts the other, there becomes a question that you have to try to answer. Is the theory incorrect? Does the theory need tweaking? Does the theory need to be thrown out? So when you have 500 million years old and it's a plus or minus 1, if you find this jellyfish at the bottommost strata, and you know that from DNA evidence it's one of the oldest organisms, then you're kind of feeling a little more confident about your results. And then you think about 1.2 million years, plus or minus 1.2 million. Does that impact your prediction that this is the oldest? If this is 501 million years, or is it 499, or is it 500? Does that really matter when we're talking about millions of years and you're comparing the age of this to the age of this? And again, if this is 429, or is it 431.2, 429.2? Is this 200, or is this 210, or is this 190,000 years old? That error is shown because of how we're using it to be not significant. The error is not significant because it doesn't impact what we're trying to do. What we're trying to do is try to get an idea of how old the rock is, where it's found, and what it does, and what the fossils, where the fossils are evolutionarily to each other. So really, when we're talking about this radiometric dating and the error that comes from it, the error really doesn't impact the results. So I hope that helps.